TRS stands for Tropical Revolving Storm. These are storms that originate near the tropics and can have sustained low-level winds in excess of 65 knots. It's the lifespan and sheer size that creates the destructive force of these storms. They can last for weeks on end before decaying and have a diameter of between 300 and 1,500 kilometres. We're now going to examine these storms in more detail. Tropical revolving storms have different names depending on their location. In the Atlantic and Eastern Pacific region, we have hurricanes. In the Indian Ocean, we call them cyclones, and in the Western North Pacific, they are called typhoons. The origins of tropical storms exist in clusters of cumulonimbus clouds that form and develop principally on the eastern sides of oceanic areas. Sometimes linked with the intertropical convergence zone, and occasionally forming on what we call easterly waves, these cloud clusters act as the atmosphere's pump, drawing moist, warm air in at low levels, with a corresponding outflow at the top of the troposphere. These inflows and outflows develop a spiralling motion, the beginnings of the storm. Only around 10% of these cloud clusters go on to produce full-blown storms. Most simply die away fairly quickly. These are the requirements for the formations and sustained development of a tropical revolving storm. The location must be between 5 and 25 degrees of the equator. The sea surface temperature must be at least 26 degrees Celsius to a depth of around 200 to 300 feet. And finally, there must be very little wind shear present, or the storm would be pulled apart. Once formed, the embryonic storm moves westwards with the upper easterly flow at around 15 knots. The warm seas over which they pass act as the initial source of energy. The formation of cloud and precipitation then releases latent heat, which adds more energy to the system as it develops. If the storm is to be maintained, it must remain over the warm ocean, where there is a continued supply of heat and moisture. If the storm tracks too far north, it moves over cooler seas, or if it moves over land, the supply of moisture is cut off. Look at this distribution map of the main tropical storm tracks around the world, and notice how the storms generally follow the peripheries of the subtropical anticyclones. There are distinct stages that can be identified during the development of tropical storms. Let's look at these now. Stage 1 is called the tropical depression. Here we see the first signs of rotation, with a lower central pressure and at least one enclosed isobar. Surface wind speeds will be 20 to 34 knots. Stage 2 is the tropical storm and starts when the system becomes more organised with surface winds of 34 to 64 knots. The storm will now be given a name. These names follow in alphabetical order, alternating between the male and female genders, starting at the beginning of the alphabet with each new storm season in each storm region. Stage 3 is the fully matured hurricane, cyclone or typhoon, depending on your location, and has surface winds in excess of 64 knots. There are several distinctive features of the tropical revolving storm. The eye and the wall are two important ones. The eye, found at the centre of the storm, has a typical diameter of 20 to 50 kilometres, and its tightening is a sign that the storm is intensifying. The eye itself may be cloudless with light winds, and it's here that we find the lowest readings of atmospheric pressure. There is a vertical wall of cloud enclosing the eye, from which bands of cloud spiral out. The strongest winds and most violent weather can be found within this wall. The sector of the wall where this is at its most extreme is where the rotating winds are travelling in the same direction as the storm itself. Flying through tropical storms is possible, but is best avoided. Advisory warnings are given when such storms exist, and satellite and radar images highlight the location of storms clearly. Marked wind shear, severe turbulence, hail and thunderstorms are just some of the many hazards that can be encountered within tropical revolving storms. We have two further depressions to look at in this lesson. Secondary lows are those that form in association with larger polar front depressions, such as we see here. The secondary low will form on the cold front as a small weakness or disturbance. Since it has been spawned within a major depression, it will move with the main cyclonic movement of its parent depression. Sometimes it develops no more than this and dies away, but on occasions this secondary depression can develop into a major feature itself and will take over as the older main depression fills and dies. The last type of low-pressure system is the tornado. Typically 100 metres in diameter, tornadoes are violent, narrow twists of wind with an intense upcurrent of air at their centre. Tornadoes only last for several minutes to a few hours, much less than other types of depression we have looked at. They are too small to be represented on weather charts, but their effects can be devastating. Winds of over 200 knots have been estimated at their centre. Tornadoes occur in many countries, typically in conjunction with cumulonimbus activity. But the best-known location is across the Midwest of the USA, in the Mississippi region. The initial spin of the air is probably caused by vertical shear, with air feeding into the system from different directions at varying heights. But strong surface heating and great instability are also required for the formation of tornadoes. Most tornadoes occur between 1400 and 2200 hours local time, with a peak at around 1700 hours, and most commonly in spring and early summer. That completes the lesson on depressions. We have examined most of the main types of low-pressure system that occur around the world. That is, apart from the large mid-latitude frontal depressions that are covered in a separate lesson. In this lesson, we will look at global climatology. We will build a model of the large-scale processes that work across the planet. From these processes, we will be able to identify large-scale pressure systems, surface winds, and eventually weather patterns. These weather patterns will be split into specific climatic zones which contain unique weather characteristics. Looking at the diagram, we can see a view of the Earth split north-south. Using this picture, we will construct and build the model of global climatology. The most fundamental aspect which controls the weather processes is the global air circulation. We have seen these air circulation cells already in other lessons, but we will expand and explain them in detail here. The diagram shows that the sun's energy is coming in at an angle of 90 degrees at the geographic equator. It is therefore this region that will receive the greatest amount of incoming solar radiation. As the land is warmed, the air in contact with it will also be warmed by conduction. This warm air rises through the atmosphere and eventually diverges on reaching the tropopause. As this air moves north and south, it eventually cools and descends. When reaching the Earth's surface, some of this air will return to the equator again and complete the circulation of one of the two cells. These are called the Hadley cells. They are the warm air circulation cells that will always be centred around the point of maximum heating, in this example, the geographic equator. But remember, the point of maximum surface heating moves north and south throughout the seasons. Now let's examine the airflow over the polar regions. The air here is very cold and tends to descend. As it descends to low levels within the troposphere, it diverges from the poles and moves steadily in the direction of the equator. This descent and divergence causes high pressure to build at the poles. At this point, we need to bring in the rotation of the Earth. If the Earth were still, the circulation would be like this. However, the circulation is complicated by the Coriolis effect, and we end up with three distinct cells like this. These are called the Hadley cell, the Ferrel cell, and the polar cell. The actual pattern of airflow is very complex, but this is an idealized model and as such is kept very simple. Remember that it is these cell circulation patterns that are the foundations of the global climatology model being constructed. From these patterns of global airflow, it is possible to identify large-scale pressure systems. Let's take a look at the junction of the two Hadley cells. Notice that the airflow at the surface is converging and rising. Eventually, this air diverges upon reaching the tropopause. This pattern of airflow creates a net loss of air in the region shown. This is because the air at the surface is entering more slowly because of surface friction. But the divergence of air at the top is much more active due to the lack of friction. We have learned from previous lessons that a net loss of air reduces the weight of the atmosphere against the surface. Therefore, a low pressure zone is created. This belt of low pressure is found all across the Earth and is called the Equatorial Low Pressure Belt, or the Intertropical Convergence Zone, the ITCZ. As we have already mentioned, this zone will move north and south as the point of maximum heating changes from season to season. But for now, let us assume it is stationary near the geographic equator. Looking at higher latitudes, we can examine another zone where the airflow is very similar to the equator. In other words, at the surface, airflow is converging and rising. Then, upon reaching the tropopause, it diverges. This location forms the second major zone of low pressure. This band of low pressure is known as the polar front, and the depressions created are called the polar front depressions. They are also called the temperate depressions or the travelling depressions. There are other areas on this diagram where the airflow is the complete opposite. If we examine the area between the Hadley and Ferrel cells, we can see that this time the airflow in the upper atmosphere is converging and descending. Then, upon reaching the surface, the air diverges. This pattern of airflow results in a net gain of air in the column shown. This is because the air at the surface is leaving more slowly because of surface friction. But the convergence of air at the tropopause is much more active due to the lack of friction. We have learnt from previous lessons that a net gain of air increases the weight of the atmosphere against the surface. Therefore, a high pressure zone is created. The high pressure systems which are found in this region are called the subtropical highs. We saw these before in the lesson on pressure systems, where they were called warm anticyclones. An example of a subtropical high lies in the North Atlantic and is known as the Azores high pressure system. There are two other regions where we see the same flow of air as the subtropical highs. If you look over the poles, we can see converging upper air and diverging surface flow. As we know, this results in a net gain of air, and therefore high pressure systems are created. These are known as the polar highs. Looking at the diagram as a whole, we can see that just from the global air circulation pattern, we have managed to construct a global pressure pattern. Next, we will look at the surface wind flow across the globe using the pressure systems and our knowledge of surface wind theory. Going back to examine the area on the surface within the Hadley cells, it is obvious here and here that air is moving from the subtropical high and into the ITCZ. But if you remember from wind theory, the air doesn't flow directly from high to low pressures. If we examine the area in the northern hemisphere between the subtropical high and the ITCZ, we know that the Coriolis effect will deflect this flow of air to the right, as shown. In the southern hemisphere, the air moving into the ITCZ is this time deflected to the left. These winds are known as the northeasterly and southeasterly trade winds. They will tend to be stronger over the sea than over the land because of reduced surface friction. When the trade winds converge, they tend to create a region where the wind is light and very variable. These regions are common over the eastern parts of oceans and are known as the doldrums. Looking at slightly higher latitudes, let's now look at what we might expect the wind to be in the region of the subtropical highs. We know that in general, the isobar spacing in high-pressure systems is quite large, and therefore the pressure gradient forces are very weak. In these areas, the surface winds are generally light and variable. In the Atlantic, these areas of light winds underneath the subtropical highs are called the horse latitudes. Looking to even higher latitudes, let's now look at the area between the subtropical highs and the polar front depressions. Looking at the side view, we can see a flow of air along the surface from the high to the low. However, only a very small proportion of air experiences this flow. The Coriolis effect is stronger here, and much greater deflection will be observed. In the northern hemisphere, the air flowing to the low pressure will be deflected to the right. As a result, the major flow of air will be westerly or southwesterly. In the northern hemisphere, this flow is massively disturbed by the major land masses, and large changes in speed and direction can occur. The surface winds here are generally considered to be variable westerlies. In the southern hemisphere, as the air moves towards the low, it will be deflected to the left by the Coriolis effect, and the surface winds will be westerly. However, there is very little land or friction to impede this surface westerly flow. As a result, these winds are stronger and more regular than those at the same latitude in the northern hemisphere. These strong westerlies in the southern hemisphere are called by the latitudes where they are found, namely the Roaring Forties and Furious 50s. The surface winds around the polar front depressions are very variable, because the polar front depressions themselves are very mobile. Next we will look at the surface winds between the polar front depressions and polar highs. Looking at the side view, we can again see airflow from the high to the low. But like before, very little air flows in this manner. Again, there is deflection from the Coriolis effect, and the resulting wind will be easterly in this area. Around the Antarctic Peninsula in the winter months, these easterly winds can get very strong, averaging up to 100 knots for days on end. The winds within the polar highs themselves should in general be fairly light, but the very mobile polar front depressions can still penetrate through the high pressure. If they do, the isobars tighten and the wind speeds increase dramatically. Having analysed the global air circulation patterns, then the pressure systems, and lastly the surface wind patterns, let's now examine the climate or weather we would expect across the Earth. The global climate will be split into zones, with each zone having unique weather characteristics, which are controlled primarily by the pressure systems found within the immediate vicinity. The first of these zones is found within 10 degrees either side of the equator, and is called the equatorial zone, or the humid tropical zone. This zone is dominated by the passage of the equatorial low pressure belt, or ITCZ. Remember that the ITCZ is characterized by active cloud development and showery precipitation, with cloud developments frequently extending to the tropopause. As we have mentioned, the band of weather will move steadily north into the northern hemisphere from December through to June, and southwards into the southern hemisphere from June to December. The ITCZ will pass through this zone twice during the year, roughly at each equinox. The animation here shows you its passage through this zone. As a result, there will be two main wet seasons. In equatorial East Africa, these rains occur from March to May and are called the long rains, and from November to December and are called the short rains. This zone is characterized by very low annual and diurnal variations of temperature, together with fairly high relative humidities. The next zone is found between 10 degrees and 20 degrees latitude. This is called the savanna. Typically, this zone experiences the passage of the ITCZ only once throughout the year, and as a result, only has one short rainy season in the summer. Look at the savanna in the northern hemisphere and notice when the ITCZ penetrates this zone. The animation will return to the June position to show the ITCZ overlying the zone. The rains will occur in summer, but only for a month or so. For the rest of the time, the dry trade wind from the subtropical highs dominates the weather. This zone is highly dependent on the transitional rains, and if they don't come one year, then the region will experience severe drought with no rain for over a 20-month period. Ethiopia and Sudan are examples of countries found within the savanna zone. The next zone to look at is the one dominated by the large subtropical highs. It is spread from roughly 20 degrees to 35 degrees latitude. This is known as the arid zone. Remember that air is being forced to descend here and will warm adiabatically. Over the land, the cloudless skies will cause surface temperatures to soar during the day and plummet at night. This massive surface diurnal variation and very low relative humidity creates a desert environment. In fact, all of our major deserts are situated within this zone. This huge temperature reduction at night can create very strong nocturnal inversions or radiation inversions. These can be hazardous to aviation, frequently causing wind shear on the approach or departure from airfields within the arid zone. Watching the animation, we can see the transition of the ITCZ and pressure systems. Notice that the ITCZ doesn't fully penetrate this zone, and throughout the year, the subtropical high is still dominating the region. The next zone is called the warm temperate zone, and is a thin band extending from approximately 35 degrees to 40 degrees latitude. Let's just examine the Northern Hemisphere one for now. Notice that in the summer months, in June and July, the subtropical high gives the zone hot, dry, cloudless skies. However, if we continue the animation now to winter, in December and January, then the fringes of the depressions influence the weather here. In winter, therefore, this zone is characterized by cooler, more moist and unsettled weather. This is typical of the Mediterranean and areas of California. The next zone forms part of the temperate latitudes and is called the cool temperate zone. This typically extends from approximately 40 degrees to 65 degrees latitude. This zone is dominated by the travelling polar front depressions and their counterparts, the cold anticyclones or ridges. These move across the globe from west to east. The weather is typically very unsettled throughout the year, but if you look at the animation, it is possible to see that in the summer months, the subtropical highs can penetrate into the lower latitudes of this zone. As a result, the summers can bring warmer, clear spells of weather. Typical areas include the British Isles, where on occasion, the intrusion of the Azores high brings a brief but welcome warm spell in summer. Other areas which have similar weather are New Zealand and the extremes of South Africa and Australia. The last major zone on this model is a polar zone and extends from 65 degrees to 90 degrees latitude. This zone is sometimes referred to as a cold desert. Typically, the air is very dry, but extremely cold. Remember, though, that the polar front depressions are very mobile and do penetrate this zone on occasion, giving very unsettled weather. The effects of the seasons are extreme, where in summer, for a few months, there can be 20 hours of sunlight, but in winter this can reverse to 20 hours of darkness. However, the effect of the sunshine is very little, because of the acute angle of the incoming solar radiation. As a result, even during the summer months, temperatures are rarely above 0 degrees Celsius. The very last zone, which does not truly form part of the model we have constructed, is called the boreal zone. This zone is only found in the northern hemisphere, over the land masses of northern North America, Scandinavia, and Russia. It approximately extends from 40 degrees to 60 degrees north. This zone is highly variable because of the way the large landmass responds to the seasons. In winter, as the land cools, cold anticyclones develop, which generally give cloudless skies and emphasize the cooling effect. Extreme low temperatures can be found especially in northern Siberia, where the temperature can be as low as -60 degrees Celsius. However, during the summer months, the land undergoes warming and the pressure pattern reverses to form gentle low pressures. This zone is characterized by the very high annual variation in temperature, and as an extreme, the highest recorded seasonal temperature change was 105 degrees Celsius in Siberia. Having seen the global aspects of surface wind, pressure and weather, let's now focus on some specific phenomena in a little more detail. Firstly, we will look at the easterly waves. On the map of West Africa, we can see that the ITCZ is well north of the equator, and the northern hemisphere is in the summer season. The development of active convective weather along the ITCZ, in particular the Niger Valley, creates groups of thunderstorms which slowly move with the easterly upper airflow. These storms or bands of weather then move off the West African coast into the North Atlantic. Collectively, these movements of active weather are known as easterly waves. About 100 or so of these waves move into the Atlantic each year, and if conditions are right, approximately 1 in 10 of these waves can develop into a North Atlantic hurricane. They can also be observed just north of the equator in South America, and these too may lead to the formation of the hurricanes which are found in the eastern part of the Pacific Ocean. There is another type of weather wave that can be found. These are known as westerly waves, and are typically the waves of weather associated with the passage of the warm and cold fronts of polar front depressions. If you remember, these move across the Earth from west to east, between the latitudes of approximately 40 to 60 degrees. This completes the global climatology lesson. The points mentioned in the lesson and the model that was constructed are vital in understanding how the large-scale weather processes work. This lesson has shown us how the theory we have learnt is brought together to understand the bigger picture of global weather patterns. There are other aspects of global weather which we have already discussed in previous lessons, namely the global upper wind patterns and jet streams. These are also vital and need to be understood in detail to gain the full picture of global climatology. In this lesson, we will examine more closely some of the weather around the world, in particular concentrating on the surface winds, the different pressure systems, and any significant weather that may be peculiar to specific areas. These weather patterns will of course change throughout the seasons, and as a result, each area will be divided into summer and winter patterns. The first of the areas to be discussed is Africa during the month of December. This is the summer season in the southern hemisphere and the winter season in the northern hemisphere. The first major significant weather feature to examine is the ITCZ. We should expect the ITCZ to be well into the southern hemisphere, on average at about 23.5 degrees south. As you can see, the ITCZ doesn't quite follow the theoretical ideal. If you notice, in the Atlantic, the ITCZ does not go south of the equator. This is partly due to the very cold Benguela Sea current, which flows from Antarctica up the west coast of Africa. This keeps the South Atlantic Ocean much colder than it would otherwise be. This colder sea prevents the ITCZ moving any further south than about 5 degrees north, and prevents the formation of any tropical revolving storms in the South Atlantic. However, on the other side of Africa, the ITCZ is over the South Indian Ocean. The tropical revolving storms, called cyclones, are very active here and frequently affect Madagascar and Southeast Africa. The ITCZ is otherwise known as the equatorial trough and is characterized by a band of fairly active cloud developments associated with convective and convergent uplift. Therefore, along the ITCZ, and even up to 500 nautical miles either side of it, expect significant cloud developments, sometimes even up to 50 or 60,000 feet. The position of the ITCZ at this time of year gives the seasonal rains to much of southern Africa in the savanna zone, like Zambia and Zimbabwe. Convective storms are very frequent in the mid-afternoon, when surface temperatures and thermal activity have reached their maximum. If you remember from the global climatology model, we would expect to find subtropical anticyclones either side of the ITCZ, as shown. Note this subtropical high-pressure belt is very dominant over the Sahara Desert and stretches out into the Atlantic, eventually joining with the Azores High. The reason the high pressure develops in December over the Sahara is because of the cooling taking place in North Africa from the very hot summer months of June and July. Remember that these systems give very clear settled weather, causing massive diurnal variation over the Sahara Desert. Looking further north, we reach the Mediterranean. If you remember from the lesson on global climatology, this area was called the warm temperate zone, and in winter the weather was cool and moist. The reason for this is that the sea maintains a slightly warmer temperature than the land masses of Europe and Africa either side. This causes a reduced pressure over the whole of the Mediterranean and is called the Mediterranean front. Thermal depressions will be generated in the Mediterranean, particularly to the eastern sides, with showery convective weather. The next element to discuss is the major surface wind patterns across the region of Africa in December. We already know that the trade winds blow from the subtropical highs to the ITCZ, and they are shown here. However, the northeast trades in the West African region are in fact monsoons. To complicate matters even further, this dry northeasterly flow has been given a local name in North Africa, the harmattan. The origin of this wind is in the Sahara, and as a result it will be relatively cool, very dry, and on occasion very dusty. The winds over North Africa will be flowing from the high pressure over the Sahara in towards the low pressures of the Mediterranean, as shown. These winds are all very similar to each other, and are named by those countries in which they are found. The sirocco blows mainly in Algeria, the ghibli blows off the coast of Libya, and the khamsin over Egypt and Malta. These winds are extremely dry and hot, and can be laden with dust and sand. The sirocco can be very active, and can collect moisture on its passage towards France, bringing low stratus and fog to the northern areas of the Mediterranean. This completes the main weather patterns over Africa in December. Let's now concentrate on what happens in June. It is the Northern Hemisphere summer and the Southern Hemisphere winter. We would expect the ITCZ to have moved slowly northwards from the December position to the position you see now. As expected, the ITCZ is well into the Northern Hemisphere and passes through Dakar, Khartoum and through to Arabia. Where the ITCZ is near the coast, very active convective weather can be expected, but further inland, the ITCZ is deprived of moisture and will therefore have very few active cloud formations. Looking either side of the ITCZ, we should expect to find the subtropical anticyclones. If you look at the northern region, the Azores High has grown massively and moved north a little to dominate much of the Mediterranean and Europe, to give warm, cloudless weather. The southern hemisphere subtropical high pressure has shrunk a little from its previous size and moved a little further north. Notice that the majority of southern Africa is under its influence. Therefore, during the winter months in southern Africa, the weather is mainly very dry and cloudless, and there are frequent grass fires. Now we have seen the pressure systems, let's focus on the major surface wind patterns. We know that air will move from the subtropical highs into the ITCZ, and we can see the northeast trades, the harmattan, across much of North Africa. However, under certain conditions over Egypt, this flow of air can develop into a significant dust storm, moving up to 15 meters per second and up to several thousand feet. It can spread as far south as Sudan, where it is more commonly known as the haboob. Looking to the southern area, we know the air will flow into the ITCZ from the southern subtropical anticyclone. For this to happen, the southeast trade winds must cross the equator. As they do, the Coriolis force causes them to be deflected to the right, and they become southwest winds. These are more correctly termed southwest monsoons. Notice the path of the southeast trade wind and southwest monsoon over West Africa. The southeast trade wind flows over the sea, gathering moisture and warming up as it moves north. This tends to make it increasingly unstable. Having crossed the equator, it gets deflected onto the landmass, which forces the air to rise, aggravates the instability, and very active weather is created, leading to torrential rains for several months. Further north, the southwest monsoon and northeast trade winds converge, forcing even more air to rise. The storms created in this process originate in the Niger Valley and are termed the West African tornadoes. This weather and the weather along the ITCZ near the coast moves out into the Atlantic because of the easterly upper winds. On satellite images, you can sometimes observe bands of weather moving from off the west coast of Africa into the Atlantic. These weather patterns are known as the easterly wave. If you remember from the global climatology lesson, these often lead to the formation of the Atlantic hurricanes. The satellite image shown here clearly identifies the convective weather of the ITCZ and the clear cloudless skies of the subtropical anticyclones either side. This is especially obvious over the southern and northern parts of Africa and the Mediterranean. The next major area we shall look at is Western Europe and the North Atlantic in December. In other words, in winter. Firstly, we shall examine the major pressure systems in the region and their effects. Notice the subtropical high pressure, the Azores High, is small and rarely affects Europe in the winter months, but is still a dominant feature in the North Atlantic. However, the major dominating systems are the polar front depressions, with their associated warm and cold fronts. They travel from west to east across the Atlantic, bringing strong winds with persistent rain and cloud. Between these depressions, we find the ridges of a high pressure or cold temporary anticyclones. These give a brief period of generally light winds and clear weather, until the arrival of the next polar front depression. In the Atlantic, there is an influence on the weather from the North American high pressure, which brings polar continental air to the western Atlantic, aggravating the formation of the polar front depressions. Occasionally during the winter months, very cold polar continental air from the Siberian high can move into Europe, giving extremely cold, clear weather. There are several important local winds in southern Europe. The first of these is the Mistral. On occasion, a high pressure can build up within Central Europe, and combined with a low pressure called the Genoa low just south of the Alps, a strong pressure gradient will develop towards the Mediterranean. This causes air to blow quite rapidly through the Rhone Valley, shown here. The other important wind is called the Bora. It flows down the western slopes of the Balkans into the Adriatic Sea. With a persistent cold anticyclone over Eastern Europe and Siberia, a cold pool of air builds up over the Balkans. Eventually it spills over the mountains, and the heavy dense air rushes down the mountain passes and can reach speeds of up to 100 knots and last for several days. This flow downhill towards the Adriatic is aided by the katabatic effect at night and the funnel effect of the local topography, causing very dangerous gusty winds that can be very hazardous to aircraft operations. Let's now look at Europe and the North Atlantic in the summer months. Notice that the dominating system is the Azores High, which has moved northwards from its winter position and intensified dramatically. This pressure system is a warm anticyclone and gives rise to very clear sunny skies, and temperatures across Europe can rise to 30 degrees Celsius or more, even reaching 40 degrees Celsius in the Mediterranean. The Azores High is a major source of warm tropical maritime air into the North Atlantic region. Polar front depressions can still sweep through the northern parts of Europe and the North Atlantic, bringing rain and strong winds, but now they are noticeably weaker and found at the higher latitudes. The very cold polar continental air affecting Europe from Siberia and Asia in winter now develops a more tropical characteristic. During the summer, a persistent northerly wind can be found to the east of the Mediterranean. This is called the Estesian. A trough of low pressure builds up over Anatolian Plateau in Turkey, and combined with generally higher pressure over the Mediterranean, a strong pressure gradient builds over the Aegean Sea. The resulting winds can intensify to gale force, particularly with local funneling and sea breeze effects. Now we look at one of the most significant regions, Southern Asia. This area stretches from the Gulf of Oman through to the South China Sea, encompassing countries like Pakistan, India, Malaysia and Korea. This area is notable because of the very direct seasonal changes in the weather. Firstly, let's examine the area in December, that is, winter. Note that the ITCZ is well into the southern hemisphere, as expected. This creates active convective weather in the South Indian Ocean from Africa through to Australia, and can create the occasional tropical cyclone. However, over Asia, the dominating pressure system is the Siberian High, whose surface outflow moves towards the low pressure zone of the ITCZ. However, as the air moves south, it gets deflected to the right, and we see the northeast trades, more correctly called the northeast monsoon. This wind is relatively cool and dry, and gives little weather across the region. However, when it passes over the sea, it collects moisture, and it starts to warm on its journey towards the ITCZ. When this happens, active weather starts to develop. By the time the air has reached the equator, it is very warm and moist. As it crosses the equator, it will be deflected left and becomes the northwest monsoon. The weather created is much more significant than that of the northeast monsoon. This time we will examine the region during the summer, in the month of June. Notice that the ITCZ has now moved well into the northern hemisphere, and its greatest northerly extent is over Korea, at about 40 degrees north. The Asian landmass has warmed significantly, and a large-scale low pressure dominates the region. The low pressure system of the ITCZ and the Asian or monsoon low will draw air from the Indian Ocean onto the Asian landmass. Notice that as the air moves north over the equator, it is deflected to the right and creates the southwest monsoon, which is like that in West Africa. The southwest monsoon warms from below as it travels north towards the ITCZ, but it also picks up tremendous amounts of moisture from the Indian Ocean. This moisture-laden air becomes very unstable, and very severe convective weather with heavy rainfall develops over southern Asia and persists for several months. This causes massive flooding as the Ganges and Brahmaputra overfill from the runoff. Many hundreds of thousands of lives have been lost in southern Asia from the southwest monsoon and its associated weather. Since the northern Indian Ocean is warming significantly in summer, tropical revolving storms can develop. These can plague areas from the Gulf of Oman to the west coast of Malaysia. In this region, they are known as cyclones. The tropical revolving storms in the Pacific, the other side of Malaysia, are known as typhoons. Typhoons are some of the most violent and active of all the tropical revolving storms, with as many as 20 to 30 storms a year. As you can see, this area of the world has a significant change in the weather from season to season. The dry and cool northeast monsoon in winter gives little weather, but the southwest monsoon in summer provides very significant risks to aviation, and this monsoon needs to be watched carefully, as do any tropical revolving storms. The Australian weather is fairly unchangeable in general, but let's have a look at December, which of course is summer for Australia. The centre of Australia is in the region of the arid zone, and therefore is dry and dusty regardless of the time of year. However, the ITCZ is well into the southern hemisphere and found just above the north coast. As a result, strong convective weather can be found along the northern coastlines. Since it is summer, in the seas around Australia, tropical cyclones will form following the paths shown. In the northwest of Australia, these have been termed the Willy Willies. The southern coastline of Australia is exposed to the trailing edges of the polar front depressions and their associated ridges throughout the year. These bring the typical weather of the warm and cold front. Between these frontal depressions are the associated ridges, which give a welcome spell of clear but cool dry weather. On occasions, a strong southerly cold wind is experienced behind active cold fronts. These are called the southerly busters. In the winter month of June, the dominating pressure systems are the subtropical highs in the interior of the continent. These give dry, dusty air to most of Australia and are a common reason for the bushfires. To the south, polar front depressions and their ridges still sweep through, bringing the usual mixture of cloud and precipitation. The phenomenon of the southerly buster can be found in southern America around Buenos Aires. However, here this cold southerly wind is called the pamperos. Most of southern America is controlled by the passage of the polar front depressions to the south and the convective weather found nearer the equator to the north. This convective weather is further intensified by the ITCZ, which dips considerably into Central South America in December. The last area to examine will be North America. Let's take a look at what the major pressure systems and weather might be in December. The main weather and pressure systems are the polar front depressions, which pass across America just north of 35 degrees north. These are active in winter, bringing snow and extensive rain towards the east coastlines. These systems have a greatly enhanced icing risk, and freezing rain is a very real hazard around the warm fronts. Thermal depressions can often be seen over the Great Lakes because the water is warmer than the land. Heavy snow showers are a persistent problem in these areas. The Gulf of Mexico has very varied weather. Occasionally, very cold polar air from the North America high can penetrate into the area, dropping temperatures to below freezing. Conversely, warm tropical air can move north from the outflow of the Bermuda High, giving rise to low stratus and fog. During June, the weather can change dramatically. Notice that the polar front has moved northward to about 45 degrees north and is also significantly weaker than in winter. Along the northeast coastline, persistent fog and low stratus develop due to the very cold Labrador Sea current cooling the general westerly airflows. Still in June, Central America warms significantly and has a lower pressure than in winter. This is called the North America or Canadian low. Within this area, expect convective cloud and thunderstorm activity from trailing cold fronts. Further south towards the Mississippi, this heating is greatly enhanced and very strong supercell thunderstorms develop, especially in spring, when both warm surface conditions and cold upper air conditions are found. These cause massive instability and spawn some of the deadliest tornadoes, giving rise to the term Tornado Alley. The Gulf of Mexico is characterized by frequent but isolated thermal thunderstorms, which are most active late afternoon and produce spectacular lightning. But the most dangerous of all the weather systems in North America are the hurricanes. In the Atlantic, these start off from the easterly waves near West Africa and grow as they move towards the eastern seaboard of the United States. They frequently pass over Jamaica and persistently cause problems to airports in Florida and around the Gulf of Mexico. However, hurricanes also develop off the southwestern coastline of North America, and although they tend to move into the Pacific Ocean, Some can curve back towards the Gulf of California. Hopefully from this lesson, you will have gained an understanding of the broad aspects of the main weather and pressure systems affecting particular areas of the globe. Remember though, these are generalizations, and the weather is something that frequently surprises us. Conditions can and do vary significantly from what we expect. Be well prepared before any flight, whether it be a long or short haul. An important point to learn is the variability of the weather. Never assume that what is forecast will always happen. Be alert for the worst, expect the worst, and you will be better prepared if the worst does happen. In part 2 of this CD-ROM, which is called Weather Briefing, you will learn how to use and then interpret the information available to you.
Remote sensing is the term given to any technique which allows measurements to be taken at a remote location without any physical sensors being located there. Many techniques are used, with more being developed, but the main ones we will discuss are radar, atmospherics, and satellite imagery. Firstly, let's take a closer look at how radar images are produced, how we should interpret them and use them to our advantage. Any type of radar works on the basic principle of a transmitter sending a pulsed beam of electromagnetic radiation and a receiver to record any reflected signals. Weather radar are specifically designed to detect precipitation. However, there are two different types. The basic and more common weather radar detect the location and extent of the precipitation and its intensity, whereas the newer Doppler radar also detects the lateral motion of precipitation particles. The time elapsed between the broadcast of the signal and the arrival of the return signal is directly related to the distance between the precipitation and the radar unit. The reflectivity, or the amount of power reflected back to the unit, provides information about the precipitation intensity. The type of precipitation can also be estimated from the reflectivity. As a rough guide, the heavier the rain, the stronger the returning signal. The rainfall radar picture usually comprises various colours, representing differing rainfall intensities, with a map overlaid for reference. Here, blue represents light rain, with the brighter reds and yellows heavier rain. It is very easy to look at a radar picture and interpret areas of precipitation and movement. However, it can be difficult to tell the difference between an echo that's precipitation and an echo that's not. The most common return from the radar is reflection from the ground. But since the ground is a stationary object, it's relatively simple to eliminate these ground echoes from the radar picture. However, precipitation may be falling in the shadow of some high ground, which cannot be seen by the radar. Another effect which regularly occurs is something called anomalous propagation, shortened to anaprop. As the beam of radiation passes through the atmosphere, it curves downwards. This is caused by the vertical variation in density of the atmosphere. It travels faster where the density is less. In extreme cases, the air near the ground may be so cold and dense that a radar beam which starts out moving upward is bent all the way down to the ground. The same can also be observed where there is a strong static stability in the lower atmosphere. The diagram shows a typical structure, with a strong temperature inversion and marked hydrolapse in the lower few thousand feet. Within the inversion layer, the radar beam is refracted downwards relative to its initial path. The result of both of these effects is an increase in ground clutter on the radar image, shown here. This will normally occur during anticyclonic conditions, or where there is a relatively deep nocturnal inversion from the surface. On this example, we can see ground return caused by hills. If you have data from more than one radar, anaprop is easy to identify, because the neighbouring radars generally won't see the same thing. Also, by comparing the radar image with surface observations, and perhaps satellite pictures, you can tell if rainfall should be expected in that area, therefore eliminating any anaprop. Sometimes interference from other radiation sources can produce errors. A good example of this can be the sun. If the radar happens to point directly towards sunrise or sunset, the reflectivity pattern can feature a ray of strong echo extending from the radar toward the sun. In this example, the spike to the west-southwest is caused by interference from another transmitter. In some areas, local wildlife can sometimes create strange and unexpected radar returns. For instance, flocking birds and insect swarms. It's usual to see a radar composite or mosaic image covering a larger area. Each radar will have a coverage of around 100 to 150 kilometers, so, by piecing several together, we can see the bigger picture. Often these will be in a movie loop, so we can determine development, speed, and direction of movement of weather. Next, let's take a look at a form of remote sensing called atmospherics. This is a technique used to identify areas of lightning and hence thunderstorm activity. As we've heard many times throughout this training course, thunderstorm activity poses a serious hazard to aviation, not only from lightning strikes, but also from associated phenomena, severe icing, severe turbulence, wind shear, and heavy precipitation, often hail. So being able to remotely identify areas of thunderstorm activity in data-sparse regions means we can identify areas which are best to avoid flying into. This tool also allows forecasters to give early warning to individual airfields, or ATC, as to the arrival of an approaching thunderstorm. The most commonly used system is called ATD, which stands for Arrival Time Difference. It was realized in the early 1920s that when a lightning flash occurs, radio waves are emitted over a wide frequency band, often called atmospherics, or simply spherics. You can quite often hear this as interference when listening to your radio. An ATD system calculates the location of remote lightning flash from the time difference of the atmospheric arriving at various pairs of detector stations. The origin of the lightning can then be calculated. Obviously, this involves precise measurements of time, and the system will use an atomic clock to synchronize all detection stations. The ATD system used by the Met Office in the UK is fully automated, and recent developments mean that lightning can be located at a rate of 8,000 flashes per hour and to a much higher degree of accuracy than ever before. This is a satellite picture of South America, with the ATD lightning data overlaid. Even halfway round the world, the system is accurate to within a few kilometres. From the calculations, a map showing lightning strikes can be produced. These maps are usually animated in steps through time to show the developments and movement of thunderstorm activity, normally updated every 5 minutes. Finally, let's take a look at satellite imagery and how to interpret various types of satellite pictures. There are two different types of orbit where the satellites are launched into, either geostationary or near-polar. The two are very different and each have their advantages and disadvantages. The geostationary type are located around 36,000 kilometers above the equator and as a result maintain a fixed position relative to the Earth. The biggest advantage is that they have an excellent field of view, covering 1/3 of the Earth's surface. Also, a series of pictures taken from a geostationary satellite can be joined together in a movie loop to show development and movement of individual cloud features. However, they do have their disadvantages as well. Since their orbit is so high, picture resolution is usually less than from other types of orbit. Also, due to their location over the equator, geostationary satellite pictures give no coverage over the poles due to the curvature of the Earth. Polar orbiting satellites, on the other hand, orbit the Earth at a height between 600 to 1,000 kilometers, and therefore produce images that are much higher resolution. They can take excellent pictures over the polar regions, and are sun-synchronous, i.e., they cross the equator at the same local time. Each equator crossing is advanced westwards by around 25 degrees, completing about 14 orbits a day. However, polar orbiting satellite pictures do have their disadvantages. Since they are in a lower orbit, their field of view is considerably less, and they will not pass over the same region again for another 12 hours. As such, cloud features cannot be tracked. So, those are the two types of orbits satellite images can be taken from, but there are also several types of pictures which can be taken from the satellite's sensors. We shall examine 3 of the more common and certainly the most useful to aviation, but be aware that there are many more. Firstly, visible images. Basically, this is the image you would view if you were on the satellite. It's measuring radiation in the wavelength 0.6 to 0.9 micrometers, the visible spectrum. The brightness in the image will depend upon the solar elevation, the viewing angle, the reflectivity of the surface, sometimes called its albedo, and also on the resolution of the image. The albedo is probably the most important, so, ignoring the others and concentrating on this for the time being, a visible satellite image can be said to be a map of the reflectivity of the underlying surface. In general, thick cloud is more reflective than thin, and so will appear brighter. Water cloud is more reflective than ice cloud and will also appear brighter. And cloud composed of small droplets is more reflective than cloud composed of larger droplets. This is why fog appears very bright on visible satellite pictures, despite the fact that it's relatively thin. So, in summary, in a visible satellite picture, low reflectivity appears black, while high reflectivity appears white, with various shades of grey being used for reflectivities between the two. Most cloud will show clearly on the image, except when the underlying ground cover is snow or ice, or when thin cirrus is viewed against a light background such as a desert or lower cloud, i.e., when there is no contrast. Another common satellite picture is of radiation in the wavelength range of 10.5 to 12.5 micrometers. That is, infrared imagery. The interpretation of the infrared image is more straightforward. The degree of whiteness can simply be taken as an indication of the coldness of the underlying surface. It therefore has the obvious advantage that it can be viewed at any time of the day and does not require the sun to be shining upon the surface, unlike visible images which can only be viewed during daylight hours. Basically, in infrared imagery, the highest radiance comes from the warmest surfaces and will appear black, whereas the lowest radiance comes from the coldest surfaces and will appear white. Intermediate radiances will appear on a grey scale between the two. This table gives an indication of how to interpret visible and infrared satellite images. If it is possible to use both images together, then this can often be very useful in identifying the location of surface fronts, upper ridges and troughs, the stages of the development of depressions and tropical cyclones, as well as individual cloud types. It's also possible to estimate the wind structure and stability of the atmosphere, the presence of lee waves, the extent of snow cover, and location of sea ice. So now let's take a look at a couple of examples and see what we can determine from these images. This is a visible image taken from Meteosat, which is a geostationary satellite centered above the equator over Africa. Here we can make a rough estimate of the surface synoptic situation. We have low pressure centers located here, here, and here. A small frontal system is located around the low pressure over southern UK, with a warm front, cold front, and occlusion. This system becomes a little more complicated because it joins up with a new one which is developing here. Now we can see the same picture, but using the infrared channel. Here we can see the same features that we did on the visible, but it is also easier to make out another frontal system to the north, which was a little vague on the visible picture. The one other type of satellite image you may come across is that of water vapour. These images are a measure of radiance in the wavelength of 5.7 to 7.1 micrometers, the region of the spectrum where water vapour absorbs strongly. Darker shades indicate that the upper atmosphere is drier, whereas lighter shading shows higher levels of humidity in this region. Water vapour images are not usually as clearly defined as other types of satellite imagery. However, there are instances where clear delineation between high and low humidities occur. One of these can sometimes be found where moist air from a large cumulonimbus cloud penetrates into the drier stratospheric air. This normally occurs in the tropics. The other occasion can be seen on the poleward side of the polar front jet, where the moist cirrus-laden air beneath the tropical tropopause abuts the dry stratospheric air overlaying the polar tropopause. So in this water vapour image, we can identify the position of the polar front jet here. Satellite imagery is not only useful for looking at cloud structures. There are several other parameters meteorologists will measure from them. For example, winds can be derived by tracking the movement of clouds from consecutive geostationary images. Also, by comparing the infrared image with the temperature profile of the atmosphere, the temperature, and hence the height of cloud tops, can be determined. Similarly, where there is no cloud cover, the sea surface temperature can be calculated. This particular image shows sea ice. You may occasionally come across satellite pictures called false colour images. These tell us exactly the same information as grayscale images, but use colours. So that's it for remote sensing. The data provided by these techniques can be a useful aid, giving more comprehensive information over a wide area, particularly in data-sparse regions.
METAR stands for Meteorological Aerodrome Report. It's a coded description of the actual weather conditions at a specific time and place. METARs are usually issued every half hour. The first group that appears in the METAR is the identification of the report type, in this case, METAR. This will be followed by the IKO location indicator. In this example, we'll use Kingsbridge. The next group is the date and time of the observation. The first two numbers represent the date, followed by the time in UTC. Details about the wind appear next. Firstly, the direction, represented by 3 digits in 10-degree intervals. This is measured in degrees true. Next, the wind speed. A gust figure, preceded by the letter G, may also appear in this group if the gust speed is at least 10 knots more than the mean. If the gust is greater than 99 knots, then the abbreviation P99 is used instead. The final letters signify which units the wind speed is measured in, either meters per second or knots. The next group may or may not appear depending on the directional variability of the wind. It signifies the extremes in the direction of the wind during the past 10 minutes. The letter V will appear between these two directions. Visibility in the METAR is represented by the next group. In the METAR, the visibility reported is the prevailing visibility. Prevailing visibility is the visibility value that is within at least half the horizon circle or within at least half of the surface of the aerodrome. Up to 10 kilometers, this is measured in meters. For example, 0450 means that the prevailing horizontal visibility is 450 meters as measured from the observing point. Once the visibility reaches 10 kilometers or more, the code figure is 9999. If the visibility in one direction which is not the prevailing visibility is less than 1500 meters, or less than 50% of the prevailing visibility, the lowest visibility observed and its general direction should also be reported. In our example, we have the prevailing visibility of 3000 meters and a minimum visibility of 1400 meters to the southwest. In some instances, we can also find the runway visibility information. This is known as RVR, or Runway Visual Range. It's only given when either the horizontal visibility, or runway visual range, is less than 1500 meters. This group starts with the letter R, and then goes on to give the runway in use, followed by the threshold visibility. In our example at Kingsbridge, let us consider a MET visibility of 2000 meters, with an RVR on runway 27 right of 1100 meters. The visibility on approach can vary significantly from the horizontal visibility, and hence, in situations of poor vis, the RVR can be very important. Note, however, that RVR is reported for the touchdown zone only. The RVR visibility can be given as P 1500 to indicate greater than 1500 meters. In some countries, a letter can sometimes come after the RVR visibility to indicate the trend that has been experienced. A U means that the visibility has increased by 100 metres or more in the last 10 minutes. A D will indicate that it has decreased, and an N that there is no distinct tendency. Occasionally, a 1-minute maximum and minimum can be shown. In this example, on runway 27 right, the RVR has a 1-minute mean as high as 1,000 metres and as low as 600 metres during the 10-minute period, and is generally increasing. The RVR value is normally measured automatically and is derived from equations that account for ambient light, runway light intensity, and is based on the expected detection sensitivity of the pilot's eye. The weather group is next, and this signifies what weather is actually occurring at or near the aerodrome at the time of the observation. Let's look at an example. The weather group can be split into 3 parts. The plus sign is the qualifier, and in this case indicates heavy. The SH is the description. In our example, SH stands for shower or showers. Finally, in the example we look at RA, which is the actual phenomena of rain. Putting this all together, we have a heavy shower of rain. That's just one weather group. There are many more. Here is the full list. It looks complicated, but it's relatively easy to work out. Let's look at each column in turn. Put simply, the first 2 columns contain letters or symbols which act as qualifiers. The last 3 columns are the weather phenomena. This may sound confusing, but all will become clear as we work through each column in turn. The first column represents the intensity or proximity. There are 4 members of this column: minus, plus, VC, or zero entry, no qualifier. We shall see how the whole weather group works later, but for now, let's consider the next column, the description. Each member of this column basically adds detail or describes the weather phenomena coming later. The small exception is TS, which represents a thunderstorm. This can be used on its own without further groups, but we'll come to that shortly. As stated earlier, the last 3 columns represent weather phenomena. We'll now look at each of these columns in turn and explain their usage. The third column in our table considers precipitation. This group is fairly self-explanatory. It contains all the precipitation weather such as drizzle, rain, snow, hail, etc. The next column looks at obscuration of the atmosphere. Again, this is fairly self-explanatory. Some of the letters used in these columns emanate from the French words for the phenomena. This may help you remember 1 or 2 of them. For example, BR, for mist, comes from the French word for mist, which is brume. The final column contains all other members of the weather phenomena which haven't already been included. This group mainly consists of more unusual events that are rarely reported, but which are very important nonetheless. This completes the whole table of the weather group of the METAR. It may appear complicated, so let's now look at how some of these symbols and letters are used. We'll look at examples, starting simply and becoming more complicated. As you use the code, you'll probably find that the more common ones are quickly committed to memory. You may have to refer to notes or another source to find the decode when encountering the more unusual groups. Let's consider the code if we have a light shower of rain. We use the following symbols and letters to represent this. Light, shower, of rain. This means that a light shower of rain is affecting the location at the time of observation. We can see from this example that it's not necessary to take a member from each column. The rules are that any one weather group must contain one or perhaps two members of the weather phenomena columns. That's columns 3, 4, or 5. There can be, but there doesn't have to be a qualifier. For instance, let's imagine there is a moderate shower at the site at observation time. The weather group that will appear in the METAR is SHRA. Let's look at some of the slightly more confusing groups. Fog is represented by FG. This can appear on its own. This simply means the observer is in fog and the visibility is less than 1,000 meters. However, there are 5 qualifiers that can also go before FG when conditions are right. They are VC, BC, PR, MI, and FZ. What do all of these mean? Well, we've looked at FG on its own. Let's take a look at the next one, VCFG, or fog in the vicinity. This means that the observer can see fog within 8 kilometers of the airfield, but still outside of the actual aerodrome boundary. BCFG is used when the observer can see at least one fog patch wholly within the aerodrome boundary. PRFG is slightly different. This would be reported when the observer can see that a fog bank has encroached the aerodrome boundary. Finally, MIFG is rather strange in that it means shallow fog at the observation point. This shallow fog, or mini-fog as it is often referred to, can be either in patches or continuous, but it must be no deeper than 2 meters. Therefore, the observer must be able to see over the top and give a visibility of greater than 1,000 meters. The final qualifier for fog is FZ, which represents freezing fog. This is a group that tells you the observer is in fog and the temperature is below 0 degrees Celsius. Fog is sometimes quite confusing, but follow the rules and you should understand what the observation is trying to tell you. The other weather group worthy of mention at this point is the thunderstorm group. The definition of a thunderstorm occurring at a location is that thunder has been heard within the last 10 minutes. Therefore, just because lightning is seen, it doesn't necessarily mean that there is a thunderstorm at any one place. Whenever a thunderstorm occurs, the letters TS are used. If there is no precipitation, then only those letters will be used. However, if there is precipitation of some kind, another 2 letters are inserted. For example, if there is rain, then TSRA will appear. Likewise, if there is hail of diameter greater than 5 mm, then you will see TSGR used. Incidentally, TSGS is for hail of smaller diameter. That's about it for the present weather group. Just one more point. Some countries have different rules, and military often differ from civilian stations, but generally there can be a maximum of 3 separate weather groups per observation. So, for example, the location may be in fog when a thunderstorm is heard. Note the 2 groups in this example are separate and do not form a single group. Cloud is the next information in the METAR. There are several cloud prefixes which are used to describe the amount of cloud in each layer. The sky is roughly divided into eighths, sometimes called octaves, and, depending on the cloud coverage, may be called few, meaning 1 to 2 eighths of cloud, scattered, meaning 3 to 4 eighths, broken, 5 to 7 eighths, or overcast, meaning complete cloud coverage, 8 eighths. The height of the cloud will follow immediately after the amount. This will appear as a 3-digit height in hundreds of feet. Cloud heights in a METAR are always measured from aerodrome level, on QFE. For example, 4 octaves at 900 feet would appear as scattered 009, and 8 octaves at 1800 feet would be abbreviated to overcast 018. If there are several layers of cloud, then these will be shown in ascending order. Higher cloud layers will only be included in the METAR if they cover a greater proportion of the sky than the reported layer immediately below. In our example METAR, we have a visibility of 8 kilometers with 2 cloud layers. The first is few at 900 feet, and the second is broken at 1500 feet. Special cloud types may appear in a METAR. If so, they will be used to denote the presence of either towering cumulus cloud or cumulonimbus cloud. Occasionally, a vertical visibility can be measured in a METAR. This is represented by VV, followed by the vertical visibility in hundreds of feet, as measured by some means. This is commonly used to describe the situation when the sky is obscured. This may be due to fog or smoke. A special code will be used in place of any cloud. Let's look at a typical example. Here we see that there is a light southwesterly wind with a visibility 100 meters in fog, and a vertical visibility that the observer could not measure. Therefore, no value was given. Occasionally, you will see this group have a figure, for example, VV002. This states that in this case the vertical visibility is measured at 200 feet. The term CAV-OK is frequently used in the METAR code to denote that cloud ceiling and visibility are OK. If CAV-OK is used, it will appear in place of visibility and cloud codes. There are 4 criteria which must be met in order for CAV-OK to be used. The first of these is that visibility must be 10 kilometers or more. Next, there must be no cloud below 5,000 feet, or the highest minimum sector altitude, whichever is the greater. No cumulonimbus present, and no significant weather. If these criteria are met, then the abbreviation CAV-OK will appear in the METAR code. Note that in the example there is no other visibility or cloud mentioned. The temperature and dew point will be the next group in the METAR code. This is simply a 2-digit number for the air temperature, a / followed by another 2-digit number for the dew point. These are measured in degrees Celsius. In this example, the air temperature is plus 10 degrees Celsius and the dew point is plus 2 degrees. If either are negative, they will have the prefix M. Now the dew point is minus 2 degrees Celsius. Temperatures are always rounded to the nearest whole degree. 0.5 of a degree would be rounded to the higher temperature. For example, minus 2.5 would be M02. The next important feature of the METAR is QNH. Remember from the lesson on altimetry how important QNH is. The QNH will be represented by the letter Q, followed by a 4-digit number representing the actual pressure value. If the QNH is less than 1000 hectopascals, then the value will be preceded by a 0. For example, a QNH of 991 hectopascals would appear as Q0991. It's important to note, however, that none of the other pressure values will appear in a METAR, only the QNH. The QNH is always rounded down for safety reasons. We saw earlier the present weather group. We'll now take a look at another group called past or recent weather. This group appears only when significant weather has occurred in the past hour, or since the last METAR, whichever is shorter. The group always begins with RE and is included if the weather phenomena is no longer occurring or has decreased in intensity. Let's see how it works. The only elements that are included are freezing precipitation, moderate or heavy drizzle, rain, snow, ice pellets, hail, blowing snow, small hail or snow pellets, thunderstorms, funnel cloud, volcanic ash, sand or dust storm. Let's look at an example. If there was heavy rain during the hour, but by the time of the observation the rain was light, the present weather would be minus RA, with RERA as the recent weather group. Note, there are no qualifiers used with recent weather groups. Basically, if any of the above criteria happen but are not mentioned in the present weather, then a recent weather group will be included. Here's another example. It's now raining heavily, but there was heavy snow earlier on in the hour. That's about it for the recent weather group, except to mention two small rules. Showers are treated as rain or snow. There can be up to 3 recent weather groups included in the METAR. Some airports will include a warning about wind shear if it has been reported by a pilot on either approach or departure, or even if it has been forecast. This will simply be denoted by the letters WS followed by the details of the report. More information about the report will be broadcast on ATIS, Volmet, or by air traffic control themselves. A trend forecast is valid for 2 hours after the time of the observation, and is attached to the end of the METAR. It gives the change in conditions expected in relation to the actual weather. However, trends are not routinely produced at every aerodrome issuing METARs. The coding used closely follows the TAF code, and for more information on this, refer to the next lesson on decoding the TAF. One major difference with the trend is that the code NOSIG is used to denote that no significant change is expected in the next 2 hours. An additional 8-figure runway state will be added to the end of the METAR when there is snow or other runway contamination. This is sometimes referred to as a snow tam and will be produced by air traffic control. It takes the form runway designator, runway deposits, extent of runway contamination, depth of deposit, and finally, the braking action required. An equals sign will appear on the METAR to denote the end of the message. Let's work through this final example. The ICAO letters identify this as being a METAR for Paris Charles de Gaulle Airport on the 8th of the month at 20 minutes past 8 in the evening, UTC. The wind direction is 150 degrees true, with a 10-minute mean speed of 16 knots. A maximum gust in the last 10 minutes of 28 knots has been recorded. The directional variation in the last 10-minute period was between due east and due south in degrees true. The visibility from the observing point was 4,500 metres in a light snow shower. The cloud was few at 500 feet and broken cumulonimbus at 1,100 feet. The air temperature was plus 2 degrees Celsius and the dew point minus 2 degrees Celsius. QNH was 989 hectopascals, with thunder in the last hour. Wind shear has been reported from runway 12. The trend in the next 2 hours is for an improving situation, with the visibility increasing to 10 kilometres or more and the cloud becoming scattered at 1,300 feet, but with cumulonimbus cloud remaining. A variation on the METAR is a special report. This will take the same format, but will be denoted by the abbreviation SPECI at the very start of the message. This will be issued when the weather conditions significantly change in the period between routine observations. This can be used to indicate either an improvement or deterioration in the weather. It's perhaps worth noting that military METARs can vary slightly from civil coding rules. They'll add a colour state to the end, a code to represent cloud and visibility conditions, blue being the best and red the worst. So, now we have an understanding of how the METAR code is constructed and how to interpret their meaning. When scanning through the METARs in flight planning, it's a good idea not just to read the METARs for the aerodromes you are taking off from, visiting or diverting to, but also a station upwind of your destination. This can give a useful guide as to the conditions that may be coming your way. But how does the METAR code relate to the weather actually being experienced at an aerodrome? In this example, the synoptic chart shows a frontal depression approaching northwestern Europe, with a ridge of high pressure following to the west. An area of high pressure is centred over the Mediterranean. Firstly, let's take a look at the weather at Brussels in Belgium. We can see that Brussels is to the east of the approaching warm front. The surface wind will be roughly southerly, around 10 knots. The cloud will be thickening and lowering as the front approaches, but at 12Z there is no weather, and the cloud base is above 5,000 feet. As such, the METAR gives CAV-OK as the conditions. It's important to note that CAV-OK gives no indication of the poorer weather conditions on the way. This is indicated in the trend. There are 4 other airports on this chart: Paris, Brest, Shannon and Madrid. Each of these stations will be highlighted and displayed. Then 4 different METARs will appear: A, B, C and D. When each station is shown, select the appropriate METAR which you feel best fits the weather at that station. The first of these stations is Paris. Please select A, B, C or D. Correct. The next station is Brest. Please select A, B, C or D. Correct. The next station is Shannon. Please select A, B, C or D. Correct. The next station is Madrid. Please select A, B, C or D. Correct. It's important to remember that these examples are generalizations. No two synoptic situations are ever the same, and conditions can, and do, vary greatly. The main reasons for this are geographic location and orography. In exposed mountain regions, winds will tend to be stronger and more gusty. Temperatures will tend to be lower, and with hill fog more prevalent. Similarly, coastal areas will be windier, and in some locations more prone to fog rolling in from the sea. In winter, showers will be more common on windward coasts than inland regions, and at certain times of the year may experience sea breezes. Inland areas tend to be more sheltered, although daytime maximum temperatures will be greater, and nighttime minimum temperatures are lower. In the summer, these areas can also be more prone to showers and extreme convective activity, such as hail, thunderstorms, and tornadoes. Sheltering effect can also be observed, mainly to the lee of high ground. Good examples of this can be found in Aberdeen, to the east of the Scottish Highlands, and in Denver, to the east of the Rockies. Another way an aviation hazard may be notified or forecast is by the use of the airfield warning system. The details of this system vary at different aerodromes, so local rules apply. However, it's still well worth being aware of these warnings, as they can add a lot to your knowledge of local conditions. This information will be covered in a lot more detail at the end of the lesson on TAFs. This now concludes the explanation on the METAR, but be aware there are many other useful sources of information which will help complement your flight briefing.
TAFs are different from METARs in that they describe the forecast conditions at an aerodrome and usually cover a period of between 9 and 30 hours. 9-hour TAFs, or short TAFs, are usually issued every 3 hours, and 12 to 30-hour TAFs, or long TAFs, every 6 hours. The TAF is issued separately from the METAR, but many of the codes and groups in the METAR are also used in the TAF. We shall only consider the main differences in this lesson. Shown here are examples of TAFs for various aerodromes. The first obvious difference is that the reported identifier is now TAF, not METAR. The ICAO location indicator of the airfield issuing the report is the same as that for the METAR. Again, we use Oxford Airport. Remember that the METAR is an indication of the weather at a specific time. However, the TAF aims to give a forecast over a period of time, so the TAF will have a different time group to the METAR. The first of these time groups is the time of issue. The date first, and then the time in hours and minutes in Zulu. So our example TAF was issued on the 13th at 0600 Zulu. In a TAF, the validity time comes next. This is an 8-digit group split into two parts. The first 4 digits are the start time of the validity period, and the second 4 digits are the end time of the validity period. So here we have a validity period starting from the 13th at 0700 Zulu and ending on the 13th at 1600 Zulu. So here is a 9-hour TAF. The decoding of the wind is the same as for the METAR, and the example shown here is a mean wind direction of 310 degrees true at 15 knots. Visibility in the TAF follows the same coding rules as the METAR, except that only the prevailing visibility value is shown. In our example, the prevailing visibility is 8,000 meters. The weather coding for the TAF is the same as the METAR, and the table shown here is to refresh your memory. However, cloud coding is slightly different than the METAR. If there is no cumulonimbus, towering cumulus, or if no clouds below 5,000 feet or below the minimum sector altitude is forecast, and CAV-OK or sky clear does not apply, then the code NSC is used. This stands for no significant cloud. Another difference is that only cumulonimbus clouds are ever reported in TAFs, whereas in the METAR, towering cumulus and cumulonimbus clouds are reported. The main TAF information ends at the cloud group. You may recall, though, that the METAR had a lot of extra information after the cloud groups, as shown here. TAFs, however, do not have any temperature and dew point, QNH, recent weather, wind shear or runway state information. Only significant changes of weather follow the cloud group. We will now look at how the significant weather changes are coded within the TAF period. The first change indicator is FM, meaning from. This is followed by a 6-digit time group. The first 2 digits are the date, and the remaining 4 digits are the time in hours and minutes. This means that from the 13th at 12:20 Zulu, certain weather changes will occur. This weather change forecast supersedes the corresponding forecast prior to this period. In this example, from the 13th at 12:20 Zulu till the end of the TAF period, the wind will change to be 270 degrees true at 17 knots with a minimum visibility of 4,000 meters and some broken cloud at 1,000 feet. This is just one type of weather change indicator that can be used. If the change cannot be accurately forecast to the hour and minute, then another code is used. The change group becoming followed by an 8-figure time group, indicates the expected start period of a permanent change in the forecast conditions. These may be regular or irregular, starting at an unspecified time within the period given. By the end of the time period given, the change should have occurred, and the conditions suggested would now prevail. Let's look at an example. The codes you see on the screen indicate that at some time on the 13th, between the 0900 Zulu and on the 13th at 1100 Zulu, the visibility will permanently become 5,000 meters in light rain. Notice that the wind information has not changed. It will still be 310 degrees true at 15 knots. The other change indicator is tempo, meaning temporarily. This is different from the becoming change indicator, in that this change may occur at any time within a specified time period, and it will therefore not be a permanent change. These temporary fluctuations are expected to last less than an hour each time, but in aggregate, no more than half the time period given. Let's look through the example on screen. Between the 13th at 1200 Zulu and the 13th at 1400 Zulu, the visibility will fall to 4,000 meters, with the weather being thunderstorms and moderate rain. There will be 5 to 7 octaves of cumulonimbus cloud at 1,000 feet. However, after 1400, the weather will return to the base conditions specified here. A probability indication can be used to assess the likelihood of occurrence and is shown by the code prob. This is expressed as a percentage of either 30% if the probability is considered low, or 40% if there is a high probability of the weather being as forecast. Probability can be followed by a time group as shown here, or by an indicator such as becoming or temporarily. One last thing must be covered before we finish the lesson. When a TAF requires an amendment, the amended forecast may be indicated by inserting an AMD after the TAF identifier, as shown here. Hopefully from this lesson, you will now be able to accurately decode the TAF message. Remember, it is a forecast of the expected conditions, and therefore essential to your MET briefing prior to your flight. If you use TAFs correctly, you'll be in a better position to make accurate and informed decisions about your flight and the expected conditions at the aerodromes you visit.
A commonly used flight briefing tool is the spot wind chart. In working through this example of a spot wind chart, we'll look at the UK version, commonly referred to as Form 214. Although each country will have their own variant on this, most are fairly similar in that they all give information regarding wind and temperature for various locations and altitudes. Although most are in a text format, the UK produces this as an easy-to-interpret graphical chart. Form 214 should be used as an everyday reference for flights within the UK and Republic of Ireland up to an altitude of 24,000 feet. At the top of every chart there will be information on validity times. Since there are 4 issues of this chart every day, it's important to ensure it covers the time period of your planned flight. The chart is a forecast of conditions expected at a set time. In our example chart, we see that it is forecast for 0900 Zulu, but valid 3 hours prior to this at 0600 Zulu, and 3 hours after at 1200 Zulu. The chart itself shows a map of the UK and Ireland overlaid with information boxes. The data within each box pertains to a specific location or spot on the map, the coordinates of which appear at the top of each box. Let's have a closer look at central England. The information for the coordinates is 52 degrees 30 minutes north, 2 degrees 30 minutes west. The information in the box is for this spot at 0900 UTC on the 28th of January 2002. The left-hand column gives the altitude in thousands of feet above sea level. The next, the expected wind direction in degrees true at that level. Next follows the wind speed in knots. And finally the temperature in degrees Celsius with either a positive or negative prefix. So, as you can see, interpreting the spot wind chart is very simple. However, if you were to plan a flight from, say, Shoreham on the south coast to Belfast in Northern Ireland, you would have to interpolate between data boxes. And if you are changing altitude, remember to check this as well. For this example flight, we'll assume an altitude of 5,000 feet, decreasing to 2,000 feet nearer Ireland. Obviously the winds will vary along the route as you go from one location to another, but also through time. However, Form 214 will give you a good estimate of the conditions you can expect to encounter along the route. This information can then be used in planning your navigation. The temperature data will give you an idea of potential icing conditions along the route. In this example, it could be a problem for the first part of the journey at 5,000 feet. But once lowering to 2,000 feet, nearer Northern Ireland, the temperature increases to plus 5 degrees Celsius. If you can recall from the chapter on icing, we said some of the most dangerous icing conditions exist when in cloud between 0 and minus 20 degrees Celsius. Try and plan not to enter these areas if possible. If you must, then prepare to use the de-icing and anti-icing equipment. Wind direction will be given in tens of degrees. Occasionally, the abbreviation VRB will be used to denote a variable wind direction. Speed will be in 5-knot increments, and temperature to the nearest whole degree Celsius. Remember, you may have to interpolate the winds between 2 spot forecasts. This will help to increase the accuracy of the flight planning and the flight itself. Although the 214 has a lot of information pertinent to flight planning, you'll still need to supplement this with other forecast charts, such as significant weather charts and the relevant TAFs and METARs. The Met Office in the UK also produce a European spot wind chart called the Form 414. The details are exactly the same, but it has an extended coverage over most of Western Europe. Spot wind information from other countries will be presented in slightly different formats, but the decoding is almost the same. Before flying, ensure you are fully conversant with the format used by your country. Low-level significant weather charts are a vital aid to successful flight planning. For flights that take place between the surface and 10,000 feet, these charts indicate in a precise and very structured format the meteorological phenomena which are anticipated in the specified area. In the United Kingdom, the chart is commonly referred to as the form 215, or just 215. It's produced every 6 hours, 365 days a year, for aircraft flying low level over the United Kingdom and adjacent areas. Also shown on the chart is the issue time, duty forecaster, and contact details. The chart is issued approximately 5 hours before the start of the validity period, and each chart is valid for a period of 9 hours. The precise period of validity of the forecast is clearly identified at the top of each chart. In this example, we have a chart which is valid between 1400 Zulu on the 10th of January till 2300 Zulu on the same day. On the left side of the chart is a schematic map. The map is a snapshot at a single forecast time, showing the positions of any fronts, and with different significant weather phenomena clearly divided into areas using black scalloped lines. Any high pressure centres are identified on the map by a small circle, and the letter H, and any low pressure centres will be identified by a small cross, and the letter L. The time at which this forecast map is valid is clearly displayed beneath the title of the chart. In our example, we have a chart map which is valid on the 10th of January at 1800 Zulu. The chart uses standard weather symbols, many of which you may be familiar with. Shown here is a list of codes and symbols. It might be worth spending time looking through the chart and committing some of the symbols and codes to memory. Let's now focus in detail on the map. As previously mentioned, frontal boundaries and areas of weather are clearly displayed. These weather areas are bound by black scalloped lines, and in some cases by the edge of the map area. Areas are clearly identified by a boxed letter. In our example here, we have the map divided up into 6 different areas. Each area is linked to the text contained in the main body of the chart by the area letter. The movement of fronts and area boundaries is identified by arrows, which indicate the direction of movement. The numbers which appear beside the arrows indicate the speed, in knots, at which the feature is moving. If a front or area boundary is stagnant or moving at less than 5 knots, then the word slow appears alongside. Let's now look at the text information on the low-level significant weather chart. As we saw earlier, this forecast information is linked to the different areas on the chart map by area letters. For each area there are 3 different columns of information. The first column describes the surface visibility and weather phenomenon, as well as the frequency and distribution of that weather. The second column contains the forecast cloud and any associated hazard. And finally, the third column details the forecast freezing levels. Let's just focus on Area A, and the first column, which forecasts the surface visibility and weather. The first line of text details the general conditions that are forecast to occur in that particular weather area. In this case, the surface visibility is 30 kilometers with nil weather. However, some variation may exist within Area A, which is different from the general conditions. More detail on these variations is provided underneath the general information using abbreviations for widespread, frequent, occasional, isolated, and localized. This will be followed by the visibility, the weather phenomenon, and more precise detail on when or where the phenomenon is occurring, such as the coasts, over land, hills, or mountains. In order to ensure some commonality between the various weather briefing tools, the coding used in the significant weather chart is similar to that used in the METAR and TAF, and shown here is a table to remind you of those codes. Let's decode the surface visibility and weather in Area A. The general condition in Area A is 30 kilometers visibility with nil weather. However, occasionally the visibility will be 7 kilometers with moderate showers of rain. In isolated areas in the west, expect 4,000 meters visibility with thunderstorms and moderate hail from 2100 Zulu. Locally, around the mountains, visibility will be down to 800 meters with moderate snow showers. There will generally be moderate turbulence, but widespread severe turbulence to the north. Lastly, in isolated areas, expect hill fog. Hill fog implies a visibility of less than 200 meters, as shown by the information in the legend. The second column of information on the chart relates to the forecast cloud and associated weather hazard. Similarly with the surface visibility and weather, the first line of the cloud forecast is the general cloud condition for the area, with variations detailed in the following lines of text. The first element in the forecast is always the cloud amount expressed as few, scattered, broken, or overcast. Next follows the type of cloud, using the standard cloud abbreviations which are shown here. Following the cloud type is the icing and/or turbulence hazard. The codes for these are shown in the legend to remind you. The next set of cloud information relates to the base of the cloud, expressed in hundreds of feet above mean sea level. And then, followed by a forward slash, are the tops of the cloud, expressed in hundreds of feet above mean sea level. At the very end, there may be further information relating to where and when particular clouds and their hazard may occur. Let's now fully decode the cloud information for Weather Area A. Generally, throughout the area, there will be scattered to broken cumulus and stratocumulus clouds. This will give rise to a risk of moderate icing and moderate turbulence within the cloud. For the icing layer, check the freezing levels for the area. Cloud bases range from 1,500 feet to 3,000 feet above mean sea level, and cloud tops range from 7,000 feet above mean sea level to above the chart level of 10,000 feet above mean sea level. In isolated areas there may be cumulonimbus clouds with bases of 1,500 feet, and tops extending to above the chart level, to the west of the area, any time from 2100 Zulu. You should note especially that when cumulonimbus clouds are indicated, it is implicit that there will be associated severe icing, severe turbulence, and hail. The last column of information in the chart relates to the freezing level. This information is relatively easy to decode and is given in hundreds of feet above sea level. For example, in Area A, the freezing level is forecast to be between 4,000 and 5,000 feet. In Area B, though, the freezing level will be between 6,000 and 9,000 feet, but as low as 3,000 to 5,000 feet to the far northeast of the area. A special weather phenomenon can be seen in the freezing information in Area D. Notice that the main freezing level is at 5,000 feet, but over land there are sub-zero layers of air from the ground to 1,000 feet. At the bottom of the chart is a brief line or two of text, which summarizes the outlook for 12 hours after the expiry of the main chart map at 1800 Zulu. This outlook does not go into precise detail about cloud heights and weather phenomena, but gives an indication of how the synoptic situation is expected to change. There is one additional element which is not shown on the chart, but can be found underneath the chart on the Met Office website. This additional element is a prognosis. The prognosis is a surface pressure chart 6 hours on from the main chart map validity time. In the case of our example map, 6 hours on from 1800 Zulu is midnight. Therefore, the chart time for the prognosis would be 0000 Zulu, as shown. Before this lesson is complete, it will be worthwhile examining a few specific items of the forecast that require further explanation. Occasionally, when conditions suit, an area will be divided into sub-areas. On the map you can see Area B and Sub-Area B1. The reason for two areas to be given similar labels is that the areas share many characteristics, but may have one or two differences. Let's have a look at these characteristics in the forecast information for the area. The general conditions for Area B, and therefore B1, are 15 kilometers visibility with possibly nil weather or light rain. However, widespread throughout the areas, the visibility will reduce to 7 kilometers with moderate rain. In isolated areas, the visibility will be 4,000 meters in heavy rain, but this would mainly be to the far north of Area B, and certainly throughout B1. The next few forecast lines do not apply to Area B1, since Area B1 does not have a warm sector, or mountains, or hills. It's important to understand the next two lines of text. Because there is no qualifier for the frequency, this weather must be assumed to be a general condition for the whole area. Therefore, generally, throughout Area B, mountain waves with a maximum vertical speed of 700 feet per minute at 8,000 feet above mean sea level are forecast. You should generally expect moderate to severe turbulence throughout the area as well. Looking at the cloud section for Area B, notice that there are local areas of nimbostratus, giving severe icing risk to the north of Area B and throughout Area B1. What you've learned during this lesson will provide you with sufficient background knowledge to understand the variety of low-level significant weather charts produced around the world. Even though there are many similarities between most of these charts, there are some differences. However, we hope that the level of understanding of the charts you have now achieved will help you use them in an effective manner. The low-level significant weather charts represent one of the best self-briefing tools for the general aviation pilot, and should form an integral part of any pre-flight weather briefing. The low-level significant weather forecast charts can be obtained from the Met Office website free of charge. For those general aviation pilots flying further afield, there is a chart which encompasses a broader area, and it's called Form 415. An example of this chart is shown on screen. Always ensure you select the appropriate chart to cover the time period you are flying. You can see that several charts are issued each day, and these have different validity times.
World, area, forecast, system, significant, weather, charts. Provide information about flight-critical weather phenomena at medium and high-level altitudes. These phenomena include the forecast locations of embedded cumulonimbus clouds, medium and severe clear air turbulence, jet streams, and other important meteorological phenomena. The WAF's SIG weather charts are produced by two World Area Forecast Centres, or WAFCs, London and Washington. The WAFCs are responsible for producing high-level SIG weather charts, that is between flight level 250 and flight level 630 for the whole world. They are also responsible for producing medium-level SIG weather charts between flight level 100 and flight level 450 for regions where there is a formal requirement for such charts. The WAFCs are not responsible for producing any low-level SIG weather charts. This is the responsibility of each state. We will now look at these SIG weather charts in some depth and understand how we can get maximum benefit from using them. Let's turn to the high-level charts. Each chart has a clearly defined legend, which contains the following information: the name of the WAFC, which produced the chart, London or Washington, a reminder that the chart is for a fixed time, the ICAO letter, which is used to designate the area, the range of heights through which the chart is valid, the time in UTC, and the date on which the chart is valid. WAF's SIG weather charts are produced every 6 hours and are valid for midnight, 06, 12 and 18 UTC every day. Since each chart is valid for a fixed time, it's the responsibility of the user to interpolate conditions between these chart times. The single letter which is used to designate the area of the high-level chart, H in our example, comes from the list of global regions which have been established by ICAO. An abbreviated name is sometimes used to designate this area rather than a letter, but this will not be visible on the legend of the high-level SIG weather chart. An abbreviated name is used on the medium-level chart legends. The other information which is displayed in the legend is largely self-explanatory, but a useful reminder that all height indications on the chart are in flight levels, all speeds are in knots, and CB, or cumulonimbus clouds, imply moderate or severe turbulence, ice and hail. WAF's SIG weather charts, which are produced by WAFC London, contain one additional legend. This highlights the flight levels between which clear air turbulence, or CAT, can be expected. In the legend, each area of CAT has a number. This corresponds to a numbered area on the chart, enclosed by a dashed line. Currently, WAFC Washington SIG weather charts do not contain this additional legend. The CAT information is placed on the chart itself, directly adjacent to the associated CAT area. This format disparity will be harmonized shortly, and charts will follow the convention used by WAFC London. Occasionally, the word prob will be assigned to an area of CAT, which implies that there is a lower probability, though still significant chance of CAT being experienced. The legends which are used on the medium-level SIG weather charts are similar to those on the high-level charts. The exceptions are the text line, which clearly highlights that these charts are valid between flight level 100 and flight level 450, and that an area abbreviation is used to highlight the chart area rather than an ICAO letter. Let's now have a look at the different phenomena which may appear on the WAF's SIG weather charts. There are a few differences between the high and medium level charts which will clearly be highlighted. We'll start with one of the most important phenomena, thunderstorms. Thunderstorms are not explicitly displayed on the charts. They are implicitly forecast whenever a cumulonimbus cloud is displayed. However, it is important to remember that only embedded cumulonimbus are displayed on WAF's charts. Open cell or isolated cumulonimbus, which are normally clearly visible in the atmosphere, are not shown on the WAF's charts. This is because they're relatively easy to spot in flight. It's the embedded cumulonimbus, which often remain invisible to the pilot until too late, that are clearly identified on the charts. As we saw earlier, any mention of cumulonimbus, or CB, implies moderate or severe turbulence, ice, hail, and the chance of a thunderstorm. Some additional information is provided in the boxes which are assigned to each area of CB. Firstly, an indication is given of the level of activity of the CBs within the scalloped area of the chart. ISOL is used to indicate that CBs will be isolated within that area. OCNL is used to indicate that CBs may occasionally be encountered within that area. Widespread implies that CBs are forecast to be widespread within the scalloped area. And finally, FRQ is used to imply that CBs are expected to be frequent. Indication is given in the CB boxes of the flight levels between which the CBs can be expected. If any of these flight levels are outside the height range of the chart, then XXX is used. For example, if ISOL embedded CB 410 XXX was displayed on a high-level chart, it would indicate that isolated embedded CBs can be expected. The top of the cloud is at flight level 410 and the base is below the chart level of flight level 250. The next phenomena which we will look at are tropical cyclones. These severe storms are shown on SIG weather charts by this easily recognizable symbol. The symbol is always accompanied by the name of the storm. In our example, Olga. Tropical cyclones are often associated with an intense area of cumulonimbus activity, which is sometimes highlighted on the SIG weather chart by the letters FRQ, indicating frequent. If moderate or severe turbulence is forecast, then this is clearly displayed on the SIG weather chart by the following symbols. Light turbulence is not explicitly forecast on the SIG weather chart. Turbulence can be experienced either in cloud or in clear air. The latter form is called clear air turbulence, or CAT. And earlier we saw how this was clearly highlighted on the charts by way of the enclosed dashed lines and the CAT legend. In cloud, moderate or severe turbulence is automatically implied on SIG weather charts whenever a CB is forecast. In addition, on the medium-level SIG weather charts, areas of moderate and severe turbulence associated with other types of medium-level cloud are always highlighted by turbulence symbols. These are included within the cloud boxes assigned to every scalloped cloud area. Moderate or severe icing is also automatically implied whenever CBs are forecast on the charts. In addition, on the medium-level SIG weather charts, moderate and severe icing is sometimes explicitly added to scalloped cloud areas when these contain cloud types with an associated icing risk. Widespread sandstorms or dust storms are highlighted on SIG weather charts only when the phenomena are forecast to significantly obscure visibility between the flight levels at which the chart is valid. The symbol which is used on the SIG weather chart is identical for both phenomena and is shown here. As we learnt earlier, the only clouds which are displayed on high-level charts are embedded cumulonimbus. On the medium-level charts, rather more cloud information is displayed. Any cloud types which are likely to have a significant impact on aviation are clearly highlighted. The impact is related to moderate or severe icing and/or turbulence. If either or both of these phenomena are forecast, then the flight levels between which they can be expected are clearly displayed in the cloud text box. In our example here, the cloud text box points to two scalloped cloud areas and indicates that broken amounts of cumulus and altocumulus are forecast within these regions. Between flight levels 250 and XXX, which is less than flight level 100, the lower range of the chart, moderate turbulence can be expected. And between flight levels 250 and 150, moderate icing can be expected. In regions of the world where there is significant convergence of nearly diametrically opposed winds, it's common to have a significant development of cloud. These regions of the world are explicitly highlighted on WAFC SIG weather charts because they are often associated with areas of significant weather and abrupt changes in wind direction. The position which is indicated on the chart is the forecast position of the convergence area at surface level. The Intertropical Convergence Zone, or ITCZ, is always displayed on SIG weather charts which cover the region of the sub-Saharan Africa. The ITCZ is clearly identifiable by way of two parallel lines and the letters ITCZ. Occasionally, the structure of the troposphere is such that there are several abrupt changes in temperature. In a sense, there are several tropopauses. The tropopause heights, which are included on the high-level WAFC SIG weather charts, are the ones which are most significant to aviation. The heights, which are displayed on the charts, relate to the lowest temperatures in the troposphere. These tropopause heights are indicated at a number of spot locations across each of the high-level charts. Tropopause heights are presented in flight levels, and when there is just one tropopause, this flight level is centered in a rectangular box. When several tropopauses are present in the atmosphere, either an H or an L is added to the tropopause box to indicate whether the upper or lower tropopause height is displayed. In these cases, the rectangular box is expanded to include the additional symbol, and the box looks more like an arrowhead pointing up or down. Jet streams are identifiable on the WAF's SIG weather charts by black solid lines, which have wind feathers indicating jet speeds at spot points, and the flight level at which the maximum speed is attained. The arrowhead on the end of each jet stream indicates the direction of movement of the flow. In our example, we have a jet stream which curves in a northeasterly direction, then gradually veers southeasterly. The jet stream reaches a peak speed of 100 knots at flight level 390. Any changes in speed along the jet stream of 20 knots are indicated by either an additional set of wind feathers, or, if there is little space on the chart, two parallel lines perpendicular to the direction of the flow of the jet. It's very common for CAT to be associated with jet streams because of the large amount of vertical and horizontal shear which occurs through the atmosphere near a jet stream. If an erupting volcano is producing enough ash to cause a significant hazard to aviation, then the location of this volcano is clearly highlighted on the SIG weather chart by this symbol. Some additional text is attached to the symbol and includes the name of the erupting volcano and its coordinates. In our example, we are using Mount Etna. Whenever a volcano symbol is displayed on the WAF's chart, and it's in the vicinity of your area of operations, then it's important to always check for any SIGMETs, which may be in force. These SIGMETs will provide up-to-date flight information regarding the nature of the ash cloud. In this lesson, we have looked in depth at the different elements of the WAF's SIG weather charts. It's important that you understand them and appreciate that they represent the best fixed time forecaster phenomena which are of interest to aviation. They should become an important element of successful flight planning.
The SIGMET is a concise message written in abbreviated plain language which concerns the occurrence and/or expected occurrence of specific en route weather phenomena which may affect the safety of aircraft operations. These messages are issued by designated meteorological watch offices which have a responsibility for flight information regions, or FIRs. Messages containing SIGMET information for subsonic aircraft are simply identified as SIGMET, whereas those with SIGMET information for supersonic aircraft during transonic or supersonic flight are identified as SIGMET SST. SIGMETs are written in a very structured way, using a lot of abbreviated plain language. Many of these abbreviations you'll have seen before when we looked at the low-level significant weather charts, but a few may be new to you. The full list is displayed here, and you may want to spend a few minutes looking through it. We'll now see how a SIGMET message is built up, by looking at the individual components of a fictitious, though correctly structured, SIGMET message. The first component of the SIGMET is the location indicator of the Air Traffic Services Unit serving the flight information region or control area to which the SIGMET message refers. In our example, Yankee Uniform Charlie Charlie. This is followed by the word SIGMET, which acts as a message identifier. After the message identifier, a sequence number is shown. In our example, the sequence number is 5. This sequence number corresponds to the number of SIGMET messages issued for the flight information region since 0001 UTC on the day concerned. It's worth noting that the sequence of SIGMET messages is sometimes indicated by a combination of figures and letters. Next follows the date and time groups indicating the period of validity in UTC of the SIGMET message. In our example, the message is valid on the 22nd of the month from 12:15 UTC to 1600 UTC. The last set of characters on the first line of the SIGMET is the location indicator of the Meteorological Watch Office which produced the message. This is then followed by a hyphen to separate the preamble from the next line of text. In our example we have Yankee Uniform Delta Oscar hyphen. This completes the first line of information of the SIGMET. At the start of the second line we have the name of the flight information region or control area for which the SIGMET is issued. In our example we've used the fictitious name Amswell FIR. This is followed by the name and description of the phenomenon which is causing the issuance of the SIGMET. This will be abbreviated plain language extracted from the table of abbreviations which we saw earlier in this lesson. Here we have severe turbulence. After the name of the phenomenon, we have an indication of whether the information is observed and expected to continue, using the abbreviation OBS, or forecast, using the abbreviation FCST. Where relevant, the time of observation in UTC is also given. We have used OBS at 12:10 in our example to indicate that the severe turbulence was observed at 12:10 UTC. The next set of information refers to the location and altitude of the observed or forecast phenomenon. Where possible, reference is made to latitude and longitude, or locations or geographical features which are well known internationally. Examples of these are forecast top at flight level 390, south of 54 degrees north, and Shannick Oceanic at flight level 250. In our example, we'll use Yankee Uniform Sierra Bravo, flight level 250, which indicates that severe turbulence was observed at 12:10 UTC over FIR Yankee Uniform Sierra Bravo at flight level 250. Movement, or expected movement, of the phenomenon is provided for by reference to one of the 8 points of the compass. Speed is given in kilometers per hour, knots, or stationary, as appropriate. We've used MOV, E, 40 kilometers per hour, in our example, to indicate that the severe turbulence is moving east at 40 kilometers per hour. Finally, an indication is made of any changes in intensity of the phenomenon, using as appropriate the abbreviation for intensifying, weakening, or no change. We've chosen weakening in our example. Let's now put all of this together. Our fictitious SIGMET reads, the fifth SIGMET message issued for the Yankee Uniform Charlie Charlie Flight Information Region by the Yankee Uniform Delta Oscar Meteorological Watch Office since 0001 UTC. The message is valid from 12:15 UTC to 1600 UTC on the 22nd of the month. Severe turbulence is expected to move eastwards at 40 kilometers per hour and to weaken in intensity. When SIGMETs for volcanic ash clouds and tropical cyclones are issued, they include an additional line of text. This line contains a brief outlook forecast beyond the period of validity specified earlier in the message. This outlook will include a trajectory of the volcanic ash cloud or positions of the tropical cyclone center as appropriate. It's important that you familiarize yourself with the structure and nomenclature used in SIGMET messages. The correct interpretation of SIGMETs forms an essential element of successful flight planning and in-flight safety.
The AirMet is a concise forecast designed for low-level aviation using abbreviated plain language. It is applicable for aircraft normally operating to flight level 100, but in some mountainous regions this is extended to flight level 150. The format of AirMets does vary from country to country, but many common elements are found in them all. In the UK, AirMets are produced for 8 different geographical areas. The information contained within these AirMets is entirely consistent with the information contained in the 215, which is valid for the same time period. The regional AirMets for areas of Scotland, North England and Northern Ireland, and South England and Wales are produced 4 times a day. The sub-regional AirMets for areas Central, South East and South West are produced 3 times a day, whilst the cross-channel AirMet is produced just twice a day. We will now take a look at a typical UK AirMet and go through it section by section. You will soon see that it looks very familiar, because a lot of the abbreviated plain text uses the same abbreviations which we saw in the lessons on low-level significant weather charts and the SIGMET. The example which we will now look at is from a Southern Region AirMet. The first line of our AirMet is a description of when the forecast is valid. In our example, the product is valid from 1100 to 1900 UTC on the 18th of the month. The next section of text is a short description of the meteorological situation which will affect the area of the forecast. Comment is usually made of any fronts which will affect the region, together with any movement. Details of air mass changes will also be given. Common, concise, plain English is used to describe the meteorological or MET situation as it is usually called. Below the MET situation is a line or two of text which details any strong wind warnings which are expected. These are added whenever the wind is expected to exceed 20 knots. This threshold applies to gusts as well as mean speeds. Just below the strong wind warning is the more general wind forecast for the AirMet region. Forecast winds are given at flight levels 060, 030 and 010. At the end of each wind forecast is a forecast of the temperature which can be expected at that flight level. Any changes in wind and/or temperature are indicated by way of abbreviated text. In this example, the wind at 1,000 feet is expected to be 20 knots from direction 330 degrees true, gradually becoming 30 knots from direction 280. The temperature is forecast to be plus 5 degrees Celsius. Immediately below the section of text which describes the winds is a forecast of the freezing level. Sometimes this varies spatially across the AirMet region, and sometimes with time. For example, when a cold front moves through the region. Any changes are highlighted by way of concise descriptive text. The main section of text, which appears immediately below the freezing level, is a description of the weather conditions forecast for the AirMet region. This region is often broken up into distinct zones, with different weather assigned to each zone area. In our example, we have 2 zones. The boundaries of these zones are highlighted by way of explanatory text. If these boundaries change with time, then movement is described accordingly. The boundary of Zone 1 in our example is given at 1500 Zulu and is a line northwest from Morecambe Bay to Waterford and is moving southeast at a speed of 40 knots. Within each zone is a description of the different weather elements which are forecast to occur. These weather elements include forecasts of visibility, weather, and cloud. The latter includes cloud bases and tops, and the quantity of cloud. These different weather elements are written in the same order as they appear on the UK Low-Level Significant Weather Chart, the 215. The same abbreviated plain language is used, which you should be becoming familiar with. We will now run through the lines of text contained in Zone 1, so that the structure of the information becomes familiar. We start with general conditions of 25 kilometres visibility in occasional rain. This is accompanied with 6 to 8 octaves of cumulus and altocumulus cloud, with a base of 2,000 feet and a top of 14,000 feet. Occasionally, the visibility will reduce to 7 kilometres in rain or rain showers, and the cloud will lower to 7 to 8 octaves of cumulus and altocumulus, with a base of 1,500 feet and a top of 17,000 feet. Isolated conditions of 3,500 metres visibility in heavy rain, rain showers, or rain and snow are forecast, and the cloud will lower to 3 to 6 octaves of stratus with a base of 800 feet and a top of 1,500 feet, and 8 octaves of cumulus and altocumulus with a base of 1,500 feet and a top of 17,000 feet. The last section of information at the bottom of each zone is a list of any specific warnings which are applicable to the zone area. These often cover aviation hazards such as cloud on hills, moderate or severe icing or turbulence, sub-zero layers, and mountain wave activity. The last line or two of text at the bottom of each AirMet is a short outlook forecast for the next 6 hours. This forecast is deliberately kept short and concise, and unless any significant changes are anticipated, is simply given as little change. When interpreting AirMets, it is essential to appreciate that the information given in each zone is a simple forecast of the anticipated conditions at a given time. Sometimes specific mention is made of the timing of phenomena. For example, isolated patches of fog with a visibility of 300 meters are expected until 0900 Zulu. Normally, though, it is the responsibility of the pilot to interpret the information in its dynamic sense. Remember that the zone boundaries are normally described relative to a time, speed, and direction of movement. You will need to gain experience in interpreting how the weather conditions may change at any place in the forecast area by interpolating the forecast accurately. As mentioned at the start of this lesson, the format of AirMets does vary considerably from country to country. Therefore, when flying outside UK airspace, it is advisable to fully familiarise yourself with the AirMet formats adopted by the Met Service of the other state. Understanding the format and language of the UK AirMets should provide you with sufficient knowledge to accurately interpret the different styles adopted elsewhere.
All weather information, from actual reports to site-specific forecasts and charts, should be readily available from your flight planning room. Otherwise, they can always be obtained by request from the local forecast office. Throughout most of Europe, information on where to find flight briefing data can be found in this handy booklet, GetMet. To find out more details of GetMet or where to order your copy, have a look at this website link. However, once you're in the cockpit, is there any way to receive updates on the weather? The answer is yes. There are several ways of receiving the most recent weather information once you're in flight. It can be obtained on request by radio, from a flight information service, or air traffic control.
Golf Romeo Charlie, Kingsbridge Tower, 0950 weather. Surface wind 280 degrees, 7 knots. Visibility 25 kilometres, nil weather. 2 octaves 3,000 feet. Temperature +15. Dew point +5. QNH 1012.
It's common practice for air traffic control to pass wind information for touchdown to you on final approach. However, if there is any information you specifically need, then simply ask.
Golf Romeo Charlie final.
Golf Romeo Charlie, clear to land. Runway 24, surface wind 270 degrees at 8 knots.
Another method is a system called Volmet. This broadcast consists of ground-to-air transmissions of Met reports and forecasts for several aerodromes within that flight information region. They are read as plain language versions of the latest METAR reports, and occasionally also include trends and RVR values. Volmet transmissions are updated whenever there is new data, usually every half hour. Some aerodromes also use a system called ATIS, which stands for Automatic Terminal Information Service. This is a recorded message of the current aerodrome information, including the latest weather. ATIS is usually broadcast on VOR or discrete frequencies in order not to interfere with air traffic operations and communications. Usually, an ATIS message will be assigned an identification letter, which will be incremented each time an update is made. There may also be two separate ATIS messages, one for arrivals and one for departures.
This is Kingsbridge Information Bravo 1350 hours weather. 220 degrees 10 knots, 8 kilometres, intermittent slight rain, 3 octaves 800 feet, 5 octaves 1200 feet, overcast 1600 feet. Temperature +12, dew point +6, QNH 1008, landing runway 26. Report information Bravo received on initial contact with Kingsbridge.
There are other systems on the market which allow you to access the latest weather information in flight. Some are integrated into the cockpit, and others download information onto a laptop or handheld computer using a modem or mobile phone. We shan't go into any more detail of these systems as they do tend to evolve and change very quickly. The most important methods which are always available to you are ATIS, Volmet, and air traffic control. But do remember, you must always ensure that you brief yourself fully on the expected conditions before you take off.